In statistics, linear regression is a linear approach to modeling a relationship between a scalar response and one or more clarifying variables. In linear regression, the relationships are modeled using linear predictor functions whose unknown model parameters are estimated from the data. Linear regression was the first type of regression analysis to be studied rigorously and to be used extensively in practical applications. Linear regression has many practical uses. It's often fitted using the least squares approach, but they may also fit it in other ways, such as by minimizing the lack of fit in some other norm, or by minimizing a penalized version of the least squares cost function, as in ridge regression and lasso. Now, given a data set of n statistical units, a linear regression model assumes that the relationship between the dependent variable y and the p-vector of regressor x is linear. Y is a vector of observed values of the variable called the dependent variable. X may be seen as a matrix of row vectors of n-dimensional column vectors, which are known as independent variables. The error value captures all other factors which influence the dependent variable y other than the regressor's x. Standard linear regression models with standard estimation techniques make a number of assumptions about the predictive variables, the response variables, and their relationship. Major assumptions made by standard linear regression models with standard estimation techniques include, but aren't limited to, weak exogeneity, linearity, constant variance, independence, and lack of perfect multicollinearity. Beyond that, several other statistical properties of the data strongly influence the performance of different estimation methods, such as the statistical relationship between the error terms and the regressors play an important role in determining whether an estimation procedure has desirable sampling properties, such as being unbiased and consistent. This arrangement or probability distribution of the predictive variables x has a major influence on the precision of estimates of beta. Sampling and design of experiments are highly developed subfields of statistics that provide guidance for collecting data in such a way to achieve a precise estimate of beta. A fitted linear regression model can be used to identify the relationship between a single predictive variable x sub j and the response variable y when all the other predictive variables in the model are held fixed. Care must be taken when interpreting regression results, as some of the regressors may not allow for marginal changes, while others cannot be held fixed. It is possible that the unique effect can be nearly zero, even when the marginal effect is large. The meaning of the expression held fixed may depend on how the values of the predicted values arise. The notion of a unique effect is appealing when studying a complex system where multiple interrelated components influence the response variable. Numerous extensions of linear regression have been developed, which allow some or all of the assumptions underlying the basic model to be relaxed. The very simplest case of a single scalar predictive variable x and a single scalar response variable y is known as simple linear regression. The general linear model considers a situation where the response variable is not a scalar. However, Generalized linear models are a framework for modeling response variables that are bounded or discrete. Generalized linear models allow for an arbitrary length function that relates the mean of the response variables to the predictors. Some common examples of GLMs are Poisson regression, logistic regression, multinomial logistic regression, and ordered logit and ordered probit. Hierarchical linear models organize the data into a hierarchy of regressions. For example, where A is regressed on B and B is regressed on C. Error in variable models extend the traditional linear regression model to allow the predictor variables X to be observed with error. A large number of procedures have been developed for parameter estimation and inference in linear regression. Some of the more common estimation techniques for linear regression are linear least squares, maximum likelihood estimation, ridge regression, least absolute deviation, and adaptive estimation. Other estimation techniques include Bayesian linear regression, quantile regression, mixed models, principal component regression, least angle regression, and the Theile-Sen estimator. Now, linear regression is widely used in biological, behavioral, and social sciences to describe possible relationships between variables. A trend line represents a trend, the long-term movement in a time series data set after other components have been accounted for. Trend lines are sometimes used in business analytics to show changes in data over time. Early evidence relating tobacco smoking to mortality and morbidity came from observational studies employing regression analysis. The capital asset pricing model uses linear regression, as well as the concept of beta for analyzing and quantifying the systematic risk of an investment. Linear regression is the predominant empirical tool in economics, and linear regression plays an important role in the field of artificial intelligence, such as machine learning. Least squares linear regression as a means of finding a good linear fit to a set of points was originally performed by Legendre in 1805 and Gauss in 1809 for the prediction of planetary movement.